So thank you for coming to my talk, and let me start by thanking the organizers for letting me present some of our recent results. This talk would be somewhat different from the previous talk, and I think rest of the talks in this session, but it would be more connected to what Kabir was pointing out yesterday. And what I'll be trying to talk about is a different way of trying to understand mechanical response in jammed granular solids, and all the references and relevant things are discussed in these two communications. And so these are the real experts in this topic. Kabir, I think, is in the audience. Okay, there he is. So all the questions, good, bad, and ugly to him. And particularly, let me point out all the hard work that Jishnu and Mike did. And there were, I'll show some experiments from the Shanghai University. Okay, let me start by pointing out almost everything that I know about granular materials. And these are these assemblies, and the constituent members, the grains, are so big that at ambient temperatures, the Brownian motion or the thermal fluctuations are irrelevant. And so we can think about them as athermal assemblies, which are at essentially zero temperatures. And these granular materials, when you pack them together under some external force, that force can lead to jamming and solidification, which is characterized by the mechanical properties of these jammed structures are characterized by this non-trivial force network. And the question that we would like to try and understand is how to think about the mechanical response of such jammed solids. And the answer that I'll try to motivate is that the mechanical response of such jammed solids is like the dielectric response of an emergent tensor electromagnetism, which I'll try to tell you a bit about. Okay, taking you back to what Kabir essentially pointed out, that we have these jammed grains, and we have at static configurations, we have force and torque balance, and we want to try and understand the force distribution across the network. And this can be done by starting with the force moment tensor at every contact, or the grain level stress tensor, which can be coarse grained to get the divergence of stress equal to the body force, and the torque balance, which is essentially the symmetric, gives rise to the symmetric nature of the stress tensor. So in spite of this random structure of the force network, the stress correlations seem to have well-behaved structures, and this is results from photoelastic disks, essentially trying to calculate stress correlations of various components of it, and they seem to show these nice structures that we would like to try and understand. So what we do for a moment, let's go back to crystalline elasticity, like for something like a diamond, where in such crystalline solids we have spontaneous broken symmetry, and the ions are periodically arranged, and this provides unique zero stress reference state. And when we try to do elasticity, we try to think about a displacement field from this reference state, and then try to take the appropriate derivatives and define the strain field. And at linear response level, we get this constitutive relation with these the rank 4 elastic moduli tensor, which is characterized by the material properties and the symmetries of the crystal. So the point that I'd like to emphasize is that there are no such unique zero stress reference configuration for jammed solids to define the displacement field unambiguously, in the sense that I can arrive at this configuration starting with zero stress reference configurations, which are widely different, or I can choose them locally, and hence the displacement field is not an observable in configuration averaged signatures. Okay, so this of course is a natural property that can be incorporated in a gauge theory, where the analogs of vector potentials are really not observables. And what I'll try to point out is that this naturally can be incorporated by thinking about this force balance condition as a Gauss's law, and not in terms of the usual elasticity, where this stress is like a symmetric tensor electric field whose divergence, the force, is like electric charge, but now the electric field is a tensor and a symmetric tensor, and the charge is a vector. And this does not require a unique reference state. Okay, and so the first step is to ask whether such things exist, and indeed these things have been studied recently in context of certain fractonic phases, and one can go over the details. Essentially, one can start by writing down Maxwell's equations for such tensor gauge theories, and the conserved quantities in such tensor gauge theories are, in addition to the charge, the dipole moment or the cross dipole moment is also conserved, and which basically means that isolated charge cannot move freely, and essentially one can create the entire analog of Jackson for these tensor gauge theories. Okay. So, so the jammed solids are a bit more complicated in this, again, because they don't exist in the in absence of external stress. So they really correspond to dielectrics of these tensor gauge theories. And the reason why it's a dielectric is that this assembly is put under boundary forces, and when since force is like the charge of this theory, this external charges acting on the boundary create an external electric field, whose in the response to which there are these contact forces that build up that builds up the force network, and which are then like the bound charges. And this is essentially the kind of analogy that goes hand in hand with the dielectric formalism that we know, where we put in external electric field and it gives rise to dipole moments, etc. So let's try to point out the static responses or correlations which corresponds to the electrostatic limit of these tensor gauge theory, and one can build up the dielectric the correspondence again following Jackson, divide up the forces into the external force and the contact forces, define the electric polarization, which is now a tensor, and an electric displacement field, and such that the dielectric electrostatics have a direct mapping to the jammed solids, where the electric displacement vector is proportional to the coarse grained stress. And one can build up this this set of mapping. Okay, so in the linear regime, which is deep inside the jammed solid, one can think about doing a linear response theory in terms of, again, usual linear dielectrics, and one can define a dielectric constant. Yeah, sure. So one can define a dielectric constant and try to connect it up with the electric field, which now has the analogy of the constitutive relation. And so this dielectric constant then plays the role of this elastic moduli, and in that sense, and it does not necessarily depend upon the material properties only, but also the properties of the force network. And this, let's try to point out, try to test with numerical and experiments on photoelastic disks. So using this, one can try to write down the low energy Landau-Ginzburg theory in terms of these electrostatic fields, and try to calculate the stress-stress correlations or the response of the stress in presence of an external point force. Okay, so these are the stress correlations in 2D, and this is what comes out of the Landau-Ginzburg theory. This electrostatics, essentially one is solving Coulomb's laws for for this tensor electromagnetism. One can do numerical calculations of the kind that Kabir was pointing out yesterday, and one can compare it with experiments on photoelastic disks in 2 dimensions. And a direct consequence of the structure of electromagnetism are these pinch point singularities that one sees at q equal to 0, and this seems to explain things quite satisfactorily, both in 2D. These are more quantitative estimates or fits, and this is in 3D. There are 21 of them, and one can try to see how good or bad this theory works. Okay, so let me end with just pointing out one more thing, the response of you put an external force in this direction and a balanced force. I'll be done in a minute. Okay, and try to calculate the difference of the stress in presence and absence of these extra forces. And this is again the comparison of the difference of the stresses in presence and absence of these test forces. And again, once one fixes the stress-stress correlations, essentially one doesn't have any more fitting parameter, and it seems to be doing sort of well with the numerical calculations. Okay, so let me end with dynamics. One can essentially extend this to dynamical situations where you this grains also has a momentum density, and that corresponds to calculating things regarding the magnetic sector. And at present we cannot derive the Ampere's law, but we just postulate it and ask what are the consequences. And among the several consequences, one is that there is an emergent wave, which because of the structure of this electromagnetism, this is a quadratically dispersing wave, and it leads to a certain density of state. And then the prediction is that in these granular materials, this wave exists, and there are these low energy density of states, and one needs to try and probe them and ask various questions, which I think we need to understand more carefully, but some of them we have some clue about. So let me summarize, let me leave up my summary here. I just want to point out the question that I think Kabir was trying to address yesterday, which is related to what happens when you drive things to crystallization. And this is, we understand parts of it, and there are new results, which I think are worth thinking. Thank you for your attention. Yeah.
Subhro, quick question. It's very nice work. In elasticity, I mean, well, unlike electric dipole, there you have the monopole terms for a electric dipole. The monopole contribution cancels. And you have the R cube term in the field, the potential expansion. So azimuthal distribution of force field for electric dipole is quite unlike the force field azimuthal distribution for elastic dipole. I mean, so this is how do you do the mapping?
So the dielectric, I guess you're talking about, is the usual Jackson dielectric. So that corresponds to the dielectric of a scalar Maxwell's equation. Okay, here the charges themselves are vectors. Okay, so this is different from, so that's why the conservation laws, etc., are very different, and what the dipole field can do here is very different from the usual Maxwell theory, which is like the vector Maxwell theory. Okay, this is a tensor Maxwell theory.
Would there be a direct analog of this fractons moving in respect?
Yeah, so
What was that?
So these are the force chains. So you see that these force chains, which is the stresses, the XX, and lines in a particular direction. So these force chains, the propagation of this is directly related to the fractons.
Being able to move in restricted.
Yeah, or linons, I think is the right.
So, here.
Sorry.
So this theory seems there's no gauge invariance, right?
Yeah.
So what is the consequence here then?
So the gauge invariance is what I started pointing out, that in a jam solid, there is no unique reference state, zero stress reference state to start with, from which you can uniquely point out what the displacement field is. So the displacement field is, actually the derivative is the analog of the vector potential. It's not observable. You start with this reference state and define your displacement field. I start with this. Okay, we should agree on the correlations. And that's essentially the
Subhro.
freedom.
So what determines the statistics here? Is there some effective tempo? I mean, like, is there equipartition, or like how?
We don't know this. So this is equal ensemble average, which seems to be suggesting that the system self-averages. Okay, so all the configurations with the same boundary conditions are averaged over equally. That's correct, Kabir, right? Yeah.
So what would be the Coulomb's law here? Like,
Yeah, so I think Kabir showed the expression. It's this. It's not as nice looking as,
but like
but it
for
is
large
1 over r
distance,
square.
1 over r
Yeah,
square.
it's
Okay.
1 over r square. That's because a single derivative is equal to the charge.
Okay.
So that's 1 over r square in 3D. Yeah, the force. Sorry. The force. Okay. Huh? Yeah, the contact forces are correlated at long distance. Yeah, because there is this local constraint.
Okay, so let's thank the speaker.
Okay.